Hello, hello. I'd like to talk a little bit about our new paper. We've just released a new paper in the December issue of Geology Today, and I'd like to give a little summary. And it's on this weird phenomenon that is called Kalima in the Canaries. It's the African winds and the dust that is blown in from the Northwest African continent over onto the Atlantic and to the Canary Islands. Let me just share my screen and we can get started here. So this is the article here, and let's just go to the Wiley page. Sorry, I should have scrolled up before. So this is in Geology Today, the journal by the Geological Society of London, and this is the front cover for the November-December issue, and that's where our article appeared. We called it African Sandstorms, Blood Rain, and Continental Mineral Delivery to the Canary Islands, and it's by myself, Juan Carlos Caracedo, and Albert Gilk from the Technical University in Munich, who did some of the analysis that we're presenting in the paper. So let's quickly move to this format here. It's a little easier to operate. So here we have the actual PDF. You can download it from the Wiley webpage, and here we are first of all giving some impression of how this actually looks when there is African winds in the Canaries. This is an image from Tenerife. This is the North Airport. You can barely see the aeroplanes here, and it's a very high particle density in the air, and this is all coming from Africa, from the red upper loose material in Northwest Africa, from the Sahara and related areas. So this produces a very thick dust cover, and this is from Tenerife. One of the main episodes of Kalima, of dust storms from Africa, was in early 2020, and this is taken in that period here, and you can see the thick dust cover on this particular car, and this is all happening within days, really. Now, I should point out that this is not only a problem, there's also good things with these dust storms, because the dust contains a lot of iron. This is why it's brown. This is why it's reddish brown. If it mixes with water, it makes what's known as blood rain. It's kind of rain running down houses, and it's got a red tinge to it. So this is where the word blood rain comes from. In medieval times, it was considered a bad omen. These days, we know that this is just a high fraction of Sahara and related area dust particles in the wind, in the air, that is then washed out with the rain. So, but let's quickly look at this map here. Well, here we have Africa, Northwest Africa. The Canaries are here under this sandstorm. This is a satellite image from late February 2020. And there you cannot actually see the Canaries because they're under this sandstorm. Giant amount of ashes blown out. Depending on the wind, there's three main routes. And the most prolific one is over the Atlantic from Africa to the Americas. There's a northerly and the southerly route. And the northerly is going over the Canary Islands, going all the way into the southern USA. The southerly route here is going mainly via the Cape Verde Islands and into the northern part of South America and the Central America. And this is actually one of the main sources for bringing in a lot of nutrients to the Amazon rainforest, because there's a lot of iron in the dust, and this is very important. Also, it's very important for the ocean basin. A lot of nutrients are being brought to the ocean floor by sinking down, and it's also a way of sequestering CO2. There's a lot of little microorganisms, calcareous microorganisms, attached to the grains, to the dust grains, and they sink down. We discuss all of these advantages in the article, of course, but also some of the disadvantages. As I said, respiratory problems in the areas affected can be a main issue. And of course, industrial issues can occur, that air filters are blocking up for factories, for vehicles and things like that. So, but what is actually in the dust? And well, let me quickly go to this map here first. Well, this is a map of Northwest Africa. This is the Canary Islands. Here's the Cape Verde Islands. And well, here's the Atlas Mountains in Morocco, and here we have the Sahara, and you see these brownish, reddish tones here. This is the source area of the dust, and it's blown over onto the Atlantic. And it's, of course, made of continental minerals because Africa is a major and very old continent. Oceanic minerals are basaltic. There's not so much quartz, for example, while continental rocks have a lot of quartz. So let's go, let's go back here. This was the plot, and this goes back to Vedipol 1969. And here in blue, we have sheet silicates. And let me go here. Sheet silicates in blue, feldspars in green. Orange is, iron titanium oxides. We try to indicate the red. And quartz is dark red, wine red, carbonates in pink, and evaporitic minerals like gypsum and halite in yellow. And then there's always some accessories that are hard to catch, but they're usually in very small quantities. So Vedipol already in the late 60s, he came up with an average Sahara sand or an average Sahara aerosol, actually. And this is 64% sheet silicates and clays. So this would be micas, clays of all sorts, kaolinite and montmorillonite, and etc., but also types of mica like muscovite, biotite, and other forms. And then here we have quartz, real quartz, 16%. And this is something we see again and again, feldspars 8%, and carbonates about 7%. And Sahara dust that was delivered to the Iberian Peninsula has been published by Rodriguez Navarro, 2018. Almost half of it is sheet silicates, clays, and micas. And then we have 23% quartz, we have 13% feldspars, 14% carbonates, and some iron titanium oxides. So when we go to the Cape Verdes, Sal Island in the Cape Verdes, this goes back to the 1980s, 65% sheet silicates and 20% quartz, 8% feldspar, 7% of the carbonates. And then if we go to Dakar, which is on the North African shore, here 71% sheet silicates, 14% quartz, and the other proportions are very similar. And then we have Kalima Dast on Tenerife, and this is the new data that we're presenting here. 58% of the sheet silicates, 20% of the quartz, 9% of the feldspar, 11% carbonates, and 1% of iron titanium oxides, and that is what makes the color red. So this is the material that's delivered from Africa, and we're discussing then what happens to this material, because first of all, the more blocky minerals, they rain out and the sheet silicates are transported further. So we have a higher rain of dust, if you will, in the Canaries that contain mainly quartz and feldspar because they are more blocky minerals, and the sheet, like the tabular crystals, they are transported further. And also the fraction, the size fraction changes with transport over the Atlantic, and the bigger kind of crystals falling out earlier. And here we have delivery that can be estimated, so you can read up the details here. But there is different layers in the air that produce different kind of concentrations of dust. But overall, it's estimated that about 260 million tons of dust are actually fluxing annually from Northwest Africa into the Atlantic basin or over the Atlantic basin, with 40 million tons being actually deposited there. Now, these are very rough estimates. They may be a little different, but it's a lot of material there. And this would mean about 0.5 grams per square centimeter. And this means per 1,000 years. And this would actually translate to about 7 millimeters of dust accumulation per millennium, per 1,000 years. So this is a lot. And if we go back to the Cretaceous time with 7 millimeters, you can actually produce the very thick package of sediment out there, and indeed close to the shelf, close to the African coast, we have several kilometers thick sediment, and then further out towards El Hierro, it gets thinner and thinner. On El Hierro, it's less than a kilometer thick, but close to the coast of Africa, it is actually up to 7 or 8 kilometers thick. And this is the material that comes since the Cretaceous from Africa. Since the Atlantic opened, this material is blown in, and it has accumulated these enormous thicknesses of sediments onto which the Canary Islands are built. So this leads us on to the main goal of the article, to discuss the context of these influences on the Canaries. And we have 3 examples where the continental material has proved to be useful, geologically speaking. And first of all, one is when we're looking at Lanzarote and Fuerteventura. This is a large ridge in the eastern part of the archipelago, and Fuerteventura has these uplifted sedimentary successions that are cropping out, initially described by Robertson and Stillman and others. And here's a few impressions. They are tilted up. They're no longer in perfect shape. They're a bit messed up and intruded by dikes, and they have fossils in there. So here's an image of a fossil, and the fossils are Cretaceous and Jurassic in age dominantly. So these are old materials, and there's these green layers here. They're rich in chloride, for example, a sheet silicate. And then we also have some more white areas here. They are quartz rich. And then we even have some zircon sands, some heavy mineral enriched bands. Because of reworking at the ocean floor, we separate them into different mineralogies. So here we're describing all of this in detail. And here we have some pictures as examples. And here we have a beautiful opportunity to see how the initial ocean island forms, because there's an age gap between the initial intrusions, the first dikes and sills intruding, and the sediments. The dikes and sills are much, much younger, and it basically means that the island that has built, the island of Fuerteventura in that case, is not part of this oceanic system. It's a much younger system. It's effectively an isolated system that was put on top of these sediments, and the sediments were broken up and partly uplifted into the now exposed island interior during formation of the island. So here we have a rather unique opportunity to study island formation, the beginning of island formation in these uplifted sections on Fuerteventura, and there's a similar section on Mayo Island in the Cape Verdes. So this is a very useful scenario, and this is one aspect here where these sediments have become useful, because they allow us to actually look into the early days of such an island formation, and the distinction between oceanic sedimentary environments and island intrusion and formation is very clear there. Another example is the floating stones of El Hierro 2011, and I talked about this before. Near the village of La Restinga was these weird rocks. Locals called them restingolites, but they were pumiceous, but they were xenolithic. They were foreign, and they had quartz as well. So this was a very distinctive tool for people who have a sense for the regional geology. Some of the people brought in from mainland Spain that were in the observatory teams, they didn't have a good clue, and they were getting very confused, because continental felsic volcanics can have quartz, but on the Canaries, felsic volcanics have no quartz. So despite the initial confusion, it was very clear very quickly that these are actually sedimentary materials brought up from the material under the islands, and indeed later on fossils were even found in those, and these were of pre-island age, so there was no doubt that these are sediments. And here's XRD diffractogram, and here we see the quartz peak, and here's some illite and chlorite, smectite, mica, so sheet silicates in abundance, and quartz, but no typical igneous minerals. So here we have no olivine, pyroxene, amphibola, feldspar, but loads of mica and sheet silicates like clays, and we have also quartz present. So this is very important. This is how they looked like. These were frothy white, very similar to the ones on Fuerteventura, but the ones on Fuerteventura were not cooked up and not frothed up. And here is the TAS diagram, total alkalis versus silica. This is the area there where the volcanics of the Canaries plot, and some really evolved rhyolites and trachytes like the ones on Gran Canaria they plot here, but even those have seen a bit of sediment contamination. And these crustal xenolith and these restingulites, or xeno-pumices as we call them, foreign pumices, they plot far to the right here towards much higher silica. So, and here we have these quartz crystals in those materials from El Hierro, and here's some fossil images. For specialists, this implies the age of the fossils can be determined, and they're very old. So here we can actually work out the onset of island formation again. How beautiful is that? We don't even need it exposed. We can actually look at this. So if you have an island forming here on a sedimentary strata and it brings up some xenolith, then you know that these xenoliths are from sediments older than the island. And here, if we have younger materials being thrown out as xenolith, we know that the island formation is indeed younger. And this allowed us to date the onset of island formation for El Hierro in a 2015 paper. And this was very important because it actually implies that here, Jurassic, Cretaceous, Paleogene, Neogene, that the islands in the western part of the archipelago over here sit on much younger sedimentary strata than here in the eastern part, and that implies there was an age progression consistent with the Hawaiian style plume model, and this is extremely important. So the old islands in the east of the archipelago, they have different materials there than the young islands in the west. And on Fuerteventura, we don't see these young sediments as part of the uplifted sequence, but here on El Hierro, we find them now as xenolith. Very elegant, I thought at the time, and I'm still quite fond of the idea. So here we can use these sediments that have been delivered by dust over many millions of years as an indirect dating technique. It's really exciting, I think. So now, the last example here is Humboldt's cone, and here we can actually date some of the features on the islands as well. Now, when Humboldt came to Tenerife, he saw some of the cones in the Orotava Valley, and there was some legends that these were very young, very recent cones, and he assigned a very young age to them. He wanted these to have erupted not so long before the Spanish conquest. He assumed the 1430s here, but he was actually visiting in 1799, so there was already a bit of time in between. And these were Aboriginal legends, so it wasn't entirely clear. There could have been all sorts of problems in terms of translation errors, etc. So, but here they are. So this is two of the cones. There was three of them. The third one has been quarried away by now. We have now worked out that the third one was sitting behind there, but this one is half quarried away. There's a hotel now, and here's a little church on top of this one. And this one here, Montaña Taora, is the critical one here now because it has a big layer of brownish, reddish material at the side of it. And this contains a high fraction of dust, Sahara dust. And indeed, it contains a high fraction of quartz, relatively speaking. It's mixed with local detritus from the sintercone, from the basaltic sintercone. So we didn't publish the analysis because it's a mixed analysis, but it clearly had quartz in there, several percent, meaning that there is African dust amongst it. And here's the issue. If this was really deposited in 1430, and we're assuming this rate I mentioned earlier, 7 millimeters per 1,000 years accumulation rate, we couldn't do that thick pile of dust in these few hundred years. It's just not going to work. So there has been an increasing suspicion that these cones are much, much older. They just look very young, but they are not potentially very young. And indeed, Juan Carlos and colleagues then eventually dated them with C49 argon, and it turns out that the cones are 30,000 years old. So this gives us a much better accumulation rate with 7 millimeters per 1,000 years. Suddenly we are getting somewhere to have these somewhat thicker deposits here at the flanks of the volcano, or of the cone of Montaña Taora. So this is very interesting, but here's another aspect, and now we are getting to the end of the article, but here's another aspect, and I really kind of thought this was rather new, and that is, well, how come these cones look so fresh? Well, they sit within the Orotava Valley, and I think what's going on is that the deposition of dust is very strong there because the winds that are pushing over the island, they will actually have to kind of deposit their load on the other side. And it might even be that the erosion was not that strong in the Orotava Valley because of the winds not being very strong. And the winds being weak, losing their load, if you will, the dust load, could actually mean that much of the erosion, much of the surface erosion in the Canary Islands is actually by wind. And here in the Orotava Valley, these cones were in a wind shadow zone, and therefore they look awfully young, but they're actually not. So this might be a very refined, I believe, explanation for how it came about that Humboldt thought they were super young cones and many workers after him, but they're actually not that young. They're actually pretty old. And here the dust was giving it away that something was wrong with the whole thing, and something didn't quite work with these dust accumulation rates. And I think it actually highlights the role of wind erosion. Because of all the dust particles in the wind, I think it's a bit like sandblasting and only features in the wind shadow, like in the Orotava Valley, they may escape strong wind erosion. So here, a rather kind of useful thing. I was always intrigued by these Kalima phenomena, and this is where we started the little article. So a lot of material comes from Africa, dust-blown material, and it provides nutrients also for agriculture and for the oceans. But geologically, there's a lot of good things we can do with them. It's not a contaminant in the sense that, of course, it's a contaminant, a continental contaminant, but because of it, we can actually learn a lot about how islands form, what the ages of the islands were, and what erosional phenomena look like, and about the age of certain features there. It helps us a lot to understand these systems better. So that was the little article, and I'll put the link into the box down there. And